My name is Oguz, and I'll be presenting the work that we've done together with Gökçe and Eno. As mentioned, we're part of the AI Labs under Artificial Intelligence Products Group, which is a part of Intel. And the specific topic that I'll talk about today is deep learning models and methods for speech command recognition. So although the workload itself is very much speech-oriented, the models and methods that I'll talk about can be applied to anything. And in this talk, I'll assume some background with deep learning. And I understand that not everyone has the same amount of knowledge on deep learning. Some people are experts, some people are newbies. So I'll try to strike a balance. But if you have any questions, please stop me and ask me about them. Also, not everyone is familiar with speech, so I'll try to do my best to not go too fast on that. So I'll start with describing the speech commands problem. What motivates that problem? What is the problem? How do you present the data? How do you prepare your data? And as with any deep learning problem, you would probably want to augment your data to get as much data as possible, and the specific network architecture that we use in this case. Then I'll talk about semi-supervised training, this technique can be applied to any problem. So not only a speech problem, but here we've applied it to a specific problem. And also population-based training, which addresses the problem of hyperparameter tuning, which is a big pain for anyone working on deep learning. So we've been seeing more and more devices that we can interact with voice. And there are speech recognition systems where you would want to translate the whole sentence or your whole intent. But there are other types of devices, edge devices, where simple chunks of audio would be effective. And in this case, you really don't want to have a large latency, or you don't want to have a processor that's burning a lot of power, right? So if you have a small robot and you want it to stop, you don't want to say stop and then 5 seconds later it actually stops. Also, you don't want your speech recognition system to drain the robot's battery, right? So the speech commands specifically targets these kinds of applications. So there is a data set that Google has curated, which I'll talk about. And the idea is to be able to recognize these commands in a very low power and a low latency way. So this is the problem, and there was actually a casual competition about 5 months ago or so on this. So Google actually invited people to compete on getting the best accuracy. So it's not very clear. So they tried to put some incentives towards getting a lightweight model, but probably that's not what happened. People just used some pretty heavy models to get very high accuracy because that's what you're measured on. So there was no way of saying the winners actually used a low-weight model, but that was the goal for the competition. And I'll talk about a little bit about the competition too. So the data set that we're going to be using, again, is the data set that was curated by Google. And what they've done is they basically crowdsourced this. So people just recorded their voices using a cell phone or any kind of device that they have available. And the data set is divided into labeled and unlabeled data. There are about 65,000 pieces of 1 second chunks of voice that's labeled. And the labels are the commands themselves. So you can say, for example, there are 10 commands that you're supposed to be classifying. They're on the right-hand side. So yes, no, up, down, left, right, on, off, stop, and go. Also, because it's going to be an always-on device, you also want to make sure that you're classifying silences and unknown words as well, so that you're not confusing. So the label data contains these commands plus another 20 different words so that we can classify them as unknowns. The unique part of this data set is that there are a lot of unlabeled data, more than 150,000 snippets of speech. So as I said, there are 30 unique words, but only 10 of them are commands. And these are, the clip lengths are all 1 second, and the sampling frequency is 16 kilohertz. And so just so that you get an idea about the problem itself, I'll play some snippets. So this is, the quality of the snippets are really very varied. So let's see here.
Yes.
So this is a pretty clean voice over here saying yes. But then there is also a voice that's kind of cut off, or you can, for example, hear there's some background noise over here, and then with some of them, the background noise is really bad. And you also get all sorts of accents, right? So with the speech command data set, you're just trying to make sure that you don't have to train on the new person. It's just, any person speaks one of these commands, it should be able to recognize it. Okay, so this is the problem. And with audio, you can represent your data in multiple different ways, right? So think about your model as a black box, right? So before you present your data to the black box, you typically do a lot of different things, like, for example, normalizing and whitening are very typical things, for example, image processing. Also, there are very typical things that are used in audio processing. You almost never put raw audio into your recognition system. But that's kind of changing right now. There are these architectures called wavenets, and they actually do a pretty good job in handling just raw audio, so you don't actually have to transform it. So we've played with some of the, let me actually try to get rid of this box over here. Okay, so if you just take the raw audio for a 1 second clip, you're gonna get about 16,000 values, right? So you can feed that in and then try to do something with that. So the problem with that is WaveNet is a pretty heavy network and doesn't really train fast. Also, if you try to use a network that's a little bit smaller, then you're not going to get as good results. So the common sense that's been in the speech domain, I think still applies over here. So either using a spectrogram or these things called MFCC features would work really well. And what a spectrogram is, it's basically translating the sound into something like what you hear in your ear. So what ends up happening in your ear is the sound comes in, and then it gets the sound gets separated into spectral components. So the spectrogram does something pretty similar. So the vertical axis is the frequency bins, and the horizontal axis is the time. So the spectrogram gives you basically frequency versus time representation of the data that's coming in. So that's a regular spectrogram. What the MEL spectrogram is, the spectrogram is just transferred into something called a MEL spectrum, which is better in capturing voice information, because not all the frequencies are distributed equally for human speech. So some frequencies contain more information, some frequencies contain less information, and the MEL spectrogram tackles that. So when you do a MEL spectrogram, you still get the same amount of values, about 16,000 values. So you haven't really done any kind of dimensionality reduction or anything like that that helps your model. But you've presented in a way that your model can now do better. You can also use MFCC features. So these are actually also hand design features that you can that are representative of your data, and that significantly reduces the amount of information that's coming in. and you can reduce it down to 640 values. And this is also typically done. But then we've also, we looked at all these different types of putting in data. And at the end of the day, we decided to go with a MEL spectrogram because it gives high accuracy, but also at the same time, it's fast enough. So it's faster than processing a raw audio, and it's more accurate than processing an MFCC feature. So once you pick your input type, like how you're going to process your input, next there are a lot of different hyperparameters that you should think about. On okay, I'm going to have a spectrogram, but also when you're coming up with a spectrogram, there are different things that you can do. For example, the image on the top left-hand side shows the spectrogram where you haven't actually put a top limit on your power. And the image on the bottom left-hand side shows when you put a 40 dB limit. So just the human eye, it looks as if the processing that's done with 40 dB is cleaner, it's nicer. But you've actually thrown out a lot of information there. So when you compare this, for example, no limit versus 40 dB, you can see on the top right-hand side, the plot with the green is the 40 dB limit, and the plot with the red is the no limit. The vertical axis is the accuracy, and the horizontal axis is the epochs. So you can see that putting no limit performs a lot better than just putting this limit. To human eye, it looks cleaner, but it's actually throwing a lot of information. There are also other hyperparameters that you need to pick. For example, when you're coming up with your bins, so you're basically doing a short times FFT in here. How many bins do you want, right? So the longer that you sample, the more you're going to capture the lower frequencies, and the shorter that you sample, you're going to capture. You're still going to capture higher frequencies, but the low frequency content is going to be gone. But then you're going to be sampling more often, for example. So that's one parameter to pick. Also, these windows you need to either overlap or not overlap. And then if you're going to overlap, how much the overlap is supposed to be. So these are all different hyperparameters. So it also makes sense when you have some sort of working model to go and explore these real quick, so that you kind of get an understanding of what the effect of these different hyperparameters are on your data. So we went through this. Exercise and then came up with certain hyperparameters. And at the end of the day, we used the hyperparameters that the red curve shows, which the actual values are not important for the purpose of the talk. And then next, I'll talk about augmentation, data augmentation. So deep learning models, most probably a lot of you know that they're pretty data hungry. The more data you have with these models, the better that they learn. And also the more data that you have, you can make it more complex on a deeper model and get better performance. In this case, for example, in images, how people do data augmentation is they'll take an image, they'll rotate it, they'll do different zooms, they'll do different crops. So basically from one image, you can come up with multiple different images. So here we do something similar. We add noise, and this noise can be, someone biking in the background or, faucet running, because it shouldn't really affect the content of the information. You can add white noise, you can add pink noise. So there are different types of noises that we add, and there are different magnitudes of how we add this noise. So in this case, we've taken one spectrogram and added noise. And you can also do time stretches. So in time, there are a lot of different variable. So I can be speaking fast, I can be speaking slow, and you want your model to be invariant to that, right? So by doing these time stretches, you also teach your model to be time invariant in your recognition. Also, you want to be insensitive to pitch, right? So some people, people have different pitches. Also, male, female have different pitches. So just taking an audio file and then doing a pitch shift makes sense. So by doing data augmentation, we can get 17 times more data from the data that we already have, just by doing these augmentations. And at some point, this becomes diminishing returns, right? So there's no clear number. In this case, we did 17 because we had computational resources. But as you have 17 times more data, your training is going to take longer. But it's not very clear how much it's helping. But at least some data augmentation is needed in any case. So after preparing the data, next step is to come up with a network architecture, and so there are some very general decisions that you need to make when you're thinking about an architecture, and then once you make that general decision, then you can go hone in to that type of architecture, and then you can start adding layers slowly. So things that you need to consider in this case were the input types. So I already talked about you can present raw audio, you can present spectrograms, you can present MCC features. So different architectures would be accepting different types of inputs. For example, you can use a 1D conf, and you can present all of these inputs. And you can use a 2D conf, but now with a 2D conf, it's not very clear how to present raw audio. And with a wavenet architecture, for example, which I'm not going to talk about, but the only thing that you can present is raw audio. So these input types have pros and cons. The network architectures have pros and cons. If you do a 1D conf, it's going to be pretty fast because it has a pretty low memory footprint. But then you're going to be sacrificing your accuracy. And if you do a 2D conf, it's going to be a little bit slower than the 1D conf, but it's still relatively fast. It gives better accuracy than the 1D conf model. The problem with the 2D conf is it's not end-to-end. Because with the 2D conf, what you're doing is you're basically treating your audio problem as an image problem, right? So what you're doing is you're cheating a little bit. You're taking your audio file, you're converting into a spectrogram, and I'm saying, okay, here's my spectrogram. Now classify this for me. And wavenets are really great, and we're actually doing some research on how to utilize wavenet for other purposes. So potentially they could be more accurate, and it's going to be end-to-end training, right? Because you're not doing any kind of hand-engineered features to these, you're just putting in the raw audio. But then these models are pretty big, so it's going to be much slower to train, and then it's going to be harder to deploy these. So at the end of the day, we actually tested all three of them, so that's how we know the pros and cons. And we decided to go with a 2D conf because it was better than a 1D conf, and it was lighter than a wavenet. And then once you decide to go with a 2D conf, sorry, go ahead.
Does running IC or PC on the data give you a feature like might be not relevant to the spectrogram or the MF?
Okay, I'll just repeat your question for everyone. So let me just get it. So the question is, can you use other types of features other than spectrograms on your data, right? Right. So specifically, the question was about independent components analysis. So definitely those could be done. The philosophy that we're sticking to is do as little as possible and let the network figure out. We're actually trying to do as much end-to-end as possible. That's why we actually explored trying to do raw audio, because then you're not actually doing anything, right? You're just letting the network take care of it. And so it can be done. It can maybe improve the accuracy, but then there'll be a lot more human engineering going into it, right? So we're trying to be as lazy as possible in this case. And I mean, it's also not very clear from the literature how much it would have helped in this case. For speech recognition, maybe this problem is very specifically treating as a classification problem because there are only 10 classes that you're supposed to. But we didn't explore it in detail. So once you decide that you have a 2D comm network, you don't actually go start with the largest thing. You just start with the smallest and simplest model that you can that will give you results. So in general, you can think about this as a black box, right? So the input is a spectrogram that's on the left-hand side, and the output is going to be something that's supposed to give you what your class is, what the probability of the class is, right? So, and typically this is done with the softmax layer. So we know the input is going to be a spectrogram, the output is going to be some sort of softmax, and you just have to fill in the middle, right? So we start with a simple convolutional net, and it will give you a certain accuracy on your validation set. And I'm kind of skipping over those parts because there's a lot of experimentation there. And then you keep adding these blocks more and more until you start seeing diminishing returns, right? So this diagram shows the final network. So there are 5 major blocks. All of these blocks are pretty much identical to each other. And within these blocks, there are sub-blocks. There are these blocks that we call attention sub-blocks, which I'll explain what they are. And then what max pool does is it just is a dimensionality reduction. You're just taking instead of so there's an average pooling layer which can decrease the dimensionality by averaging pixels that are right next to each other. But then there is also a max pool, which just takes a max value, and max pool is known to work better in these cases for dimensionality reduction. And the attention subblock specifically is basically made out of simple convolutional layers. So the 2 convolution layers that are made out of are called the filter and the gate. So think about the regular convolutional layer, which we call the filter, and it has a RailView output. But then we also have a parallel path to this. This is also a convolutional layer. But the output for these convolutional layers, the output feature maps, are actually mapped from 0 to 1. So what this allows the network to do is it can, and then after we pass the data through the filter and the gate, we would multiply them. So basically, you're doing a pixel-wise multiplication at the end of these 2 output feature maps, and the 0 or 1 gate output can basically turn on and off the outputs of your filter, right? Of your output feature map. So this general concept is called attention, and it's a kind of a hand-wavy term. So we saw that adding this attention module actually increased our accuracy. Batch norm is very typically used. It allows the gradients to flow a lot better, and your network behaves a lot better with the batch norm. That is good.
A little more detail on this gate. How is this gate
activated? Right. So the question was, could I give some more detail on the gate? So gate is nothing different than a convolutional net, right? So so you can think about your filter outputs some sort of output feature map, right? Then if you want to pick these pixels one by one, what would be nice would be to have another feature map that's the same size, but it just has values between 0 and 1. And then once you do pixel-wise multiplication between these, it would have acted like a gate, right? Because if there were 0, it wouldn't pass, and if it was 1, the information would pass. And the easy way of doing this is just to have your neural nets also to learn that gating layer, right? So your output feature map is there's yet another convolution neural net which is learning these gates, and then all you're doing is you just element-wise multiplying. Does that make sense? Or
so basically, the gate is nothing but a convolution.
correct.
How many layers does it have?
So the filter and the gate is just one conv layer. And then depending on where in the pipeline it is, it can have different numbers of filters, basically. Right? So sorry?
The gate is also learned.
Yes, exactly. Gate is also learned. Yeah, everything here is learned. No, there are no LSTMs or RNNs here. But then, you know, LSTMs, for example, use the idea of gates as well, right? Yeah. I mean, this is a similar idea. You know, whenever people have like an output between 0 and 1, and then they multiply it, they would call it a gate because it's basically that's what it's doing. Right? It's either cutting out the information or letting the information pass.
So on the audio data, do you use any windowing? Like, or do you just use bare windowing?
Right, so the question is, do we use any windowing on this? So typically on speech recognition systems, you have to use windowing, right? Because you don't know the size of your input. But in this case, with speech commands, it's 1 second. We know that for sure. So here we're just not using any windowing, we're just putting the input and it's fixed in size. So there's no windowing that's used in this case. Also, the attention subblock also has a dropout layer, and dropout is also used very typically in deep learning as a regularizer. So, the network is made out of these very small components that are kind of stitched together to make this one large big thing. But then, you know, how you arrive at this is really by going from bottom up. And you can see that once you break these down, for example, once you have this one block, all you need to do is say, okay, if I add another block, is it going to be better or worse? So this is kind of typical practice in deep learning, which is a little bit disturbing, right? Because experimental, you kind of have a feeling about where things will go, but then the only way to actually get a model working is to do a lot of trials and errors, and then try a lot of mistakes. So this is the final network architecture that we came up with. And when we used this, it was still not giving us super good results. So we took a step back and said, okay, we are using all these labels and then we're training our model in a supervised manner. But what if we could somehow leverage these unlabeled data, right? So the hypothesis is that if we could somehow put in the unlabeled data and then train our network with that unlabeled data as well, our accuracies would go up. And that brings us to this semi-supervised training part of the talk. So this technique, you can use it with any kind of model. So it's not specific to this model. So I'll try to give you an intuition about what's happening with the semi-supervised learning stuff. So here, just think about a supervised learning problem that you have 3 classes, right? Class A, Class B, Class C, and then let's assume that you know that the correct label is Class A. So when you're training iteratively, right? This is a deep learning model, and then you forward propagate your input, you get a prediction, right? And then let's just represent that prediction with the gray dot over here. Dots, and then these are the 3 classes. So essentially, what you're trying to do when you're training is when you back propagate your loss, when you penalize your network, you're trying to pull the prediction towards Class A, because you know that the correct class is supposed to be Class A. So this is typical supervised learning. So if you wanted to do something semi-supervised, what can you do? So in a semi-supervised setting, you can use some of the unlabeled data. So one trick that you can do is you can put your unlabeled data, right? Let your network predict something, and that's given by the gray dot. And then you can add noise to your input. And you know that it's supposed to be the same classification. It's supposed to be the same class. And now your network is going to output yet another output that's represented as a yellow dot, right? So what you do is you say, okay, I want you to pull the prediction from the noisy input towards the prediction for the clean input, right? So now you haven't used any of your labels. You've just used the knowledge that your network has to use your to use your unlabeled data. The danger with this is that if your prediction from your clean data was not good to start with, your network is going to get very confused, and now you might start getting drifted around some unknown places, and then your network actually may start performing worse. So something better to do is to actually feed in two different noisy inputs, and then you know that there's actually supposed to be in the same place, right? Because you're just the fundamental input is the same. It's just that you're adding different noises. So what you do is that you take those two noisy inputs and then you just say, okay, I want you to actually be in the same place. So that's one way to use your unlabeled data. Another way to use your unlabeled data is to use a teacher. So I'll explain how you come up with a teacher, but let's just assume that your network had another copy that was just a little bit better than its current state. So we'll call that the teacher. And what you can do is, bit by bit, you can feed the information to the student model, and then you can feed the information to the teacher model. And these will give very close results, but teacher will be just a little bit better than the student. And I will just say, okay, the teacher pull the output of the student model towards the teacher, right? So here again, we didn't know that the correct label was class A because it was unlabeled data, but because we had a teacher, we were able to actually use that label. So, so these guys who actually came up with this method, they just, I mean, these two were known to be working. So they came up with a method to combine these two, and then it was presented at NIPS last year. It's called Mean Teachers Are Better Role Models. And the mean teacher just means that it is actually a really mean teacher because it's actually an exponential moving average of your original model that gets translated into a teacher. Sorry, go ahead.
My question is about from my understanding, the network should be the input layer should be the audio, either be the raw audio or the spectrum. What is the output node
Right.
of the network?
Okay.
I guess it might be some words like yes or no, or turn out nice, some English words or some words.
Yeah, so I probably wasn't very clear. Maybe I just skipped over it very fast. So the question is, we know that your input is a spectra, what's your output? So how do you actually capture the output? So with the output, you put what's known as a softmax layer. So you have 12, you know that you have 12 classes. So the network would,
how many nodes of the final layer? I mean the output.
12, because we have 12 classes, right? So we have to classify between yes, no, up, down, and then silent and unknown. So there are 10 commands, and then silence and unknown.
So each network only will 10 or 12 commands, is that correct?
So there's only one network, and then the output has 12 outputs.
12 for output, from my understanding, should only handle the 12 commands.
Correct. So it's not actually outputting, a specific, it's not saying, it's not like a typical speech recognition system where, you're stitching together letters. It's just saying it's left, it's right.
Okay. So
it's a classification problem.
Each network only handle 12 commands, right?
Yeah, that's the problem, yes.
Okay, so as we know, if we want to enact the command set, so we might either by enacting the network and more output in the final layer.
That's correct. So if you wanted to get, so I think your question is, what if you had more commands, right? What if you don't have 10 commands, but
the first is what if we have more commands? Second, if we have, for example, thousands of commands, how to handle this?
Right. So I think at some point, you need to start changing your approach to the problem if you start having more and more words, right? Because here, we have the luxury to treat this as a classification problem because there are only 10 classes. I'm assuming that as you get up to like hundreds of classes, then this will probably start breaking down, and it's better to go with a more traditional, maybe like a deep speech model or some sort of INN-based model, which is actually spitting out letters rather than just specific classes, right? I think the approach of using classification, I would feel probably comfortable up to like 40 maybe, but after that, I wouldn't recommend it. But in this case, because these are commands, hopefully you're not going to have too many commands to give to your robot or whatever device that you're talking to. So this is specific. I mean, if you want your device to recognize thousands, probably the right approach is to let it send that information to the cloud and then work and then have that information being processed on a lot stronger model, right? And then you can tolerate the latency in that case. Right. So this method basically combines these two approaches, and I'll talk about how specifically this is done. So I try to give you some intuition. So specifically, this is the implementation. Sorry, go ahead.
It's just a question about it. So you know how usually the sound, is it guaranteed that the entire word is caught in that 1 second? Right? Because like there's a possibility that like half the word could be caught.
Yeah, no, it's not guaranteed. I mean, I actually try to give some examples. So the quality of the clips are varying. So some people just have recorded like maybe half of the word. But then what you can do, and also the data set itself is not perfect. Like you can actually find some clips that are like less than 1 second or a little more than 1 second. So there is this step where you actually go and make sure that they're 1 second. If they're not, you kind of like either clip it or pad it. Yeah. But yeah, there is no guarantee that it's actually gonna. They told the folks who recorded these to have it within that second, but not everyone did that. So you do get these variabilities. Yeah. Here you just see a pipeline for a typical supervised learning system, right? So you put an input, and your model is basically some model, and in this case, let's say it's parameterized by data. We're just treating it as a black box, so you can put any model that you want in there. And then here we have an output that's a softmax, and in this case, there are 12 different classes. And in this specific case, if you're doing supervised learning, you know your label, right? And then you just take that label and then backpropagate that loss. So the trick over here for coming up with a teacher is you do a exponential moving average over time. So as your model is training, you just take these parameters and you do a moving average on them, and then you come up with another network. So the idea is that this other network would, because it's a moving average of the original network, it will actually perform just a little bit better than the current model. And then the intuition for this is that anytime you have an ensemble of models, it actually does better than a single model. Right? So you're kind of doing that in this case. So now that you have a teacher network that's just a little bit better than the student network, what you can do is you can take the input that we fed in, but change it a little bit, put a little bit of noise, pass it through the teacher network, right? So so in this case, the input that you're putting into your teacher network is some input that you don't know the label for, right? So you can push that through the teacher, and the teacher is going to tell you that, for example, the word is on. And then you're going to trust your teacher, and you're going to penalize your student network by being different than your teacher network, and that's called the consistency loss. So now you have two different losses. You have a classification loss for the stuff that you know the label to, and you have a consistency loss for the data that you don't know the label to, right? And this allows you to actually use all your unlabeled data here as well. So this is a pretty neat trick, and actually it does boost your performance a lot. So if you have any problem that you have a lot of unsupervised data, I would definitely recommend using this. And here are the results. The figures on the left-hand side are the confusion matrices. The top left one shows for the supervised case, and the bottom left-hand side shows for the semi-supervised case. The vertical axis is the ground truth, and the horizontal axis is the prediction for the network. You could see that the semi-supervised method is doing especially better in the silence and unknowns in this case. And when you look at the overall accuracy, that's shown in the plot on the right-hand side. The vertical axis is the accuracy, and the horizontal axis is the number of epochs for the training. You see that the semi-supervised technique is doing a lot better than the supervised training. And so in the Kaggle competition, this specific model gave about 90% accuracy, and then the best model was 91%. So this is pretty decent result because typically in Kaggle competitions, people kind of come together and then put all their models and then they do an ensemble. So it's like a big mess. But here it's like a single model that's trained end to end. So it does, in terms of accuracy, it gives pretty good results. Yeah, sure, go ahead.
Teacher network, do you update teacher network as well?
Right. So the teacher network is only updated through the student. So the gradients never flow through the teacher network. The teacher network is only used to do an inference. So after each iteration, you'll just take the student weights, and then you'll do an exponential moving average to come up with the teacher network. And then there are some hyperparameters there that you need to pick. For example, how much the teacher would remember the past, right? So in certain cases, you don't want to remember, especially in the beginning, right? You don't want to accumulate the teacher fast, so you just let it forget the past really quick, and then you kind of like ramp up that parameter alpha slowly, basically.
Okay, so teacher-specific collection of students.
Correct, exactly. So yeah, the teacher would be a collection of the past students. It will be more like an ensemble of the past students.
Then is there any possibility of divergence? As students go bad, then
yeah, so the question is there possibility of divergence if the students were bad? Yeah, definitely, I think so. I mean, if you don't have enough label data, and if your students are doing crappy and you're just like accumulating that error, it might go to some completely different places. But I haven't played around with how much label data that you would need. But in the paper, they show some pretty impressive results on images. So they've only explored the I think only with the 10% of the data that's normally available, you can do as good as like 100% of the data. Yeah, sure.
During your evaluation for score was 98%. So I understand that that's 98%, 89% correct, right?
Yes, yeah. So it will get it correct 89% of the time.
89%. Okay, that's fine. What was the lowest SNR, like signal to noise ratio, during the testing?
What do you mean by the SNR?
SNR, signal to noise ratio.
Right. The signal to noise ratio of what?
And you mix in certain amount of noise.
Right.
And then you measure powers.
Yeah.
Signal.
So are you talking about the noise that we have added, or
Yes,
yeah?
like typically, like any recording, like even the most clean one, will still contain some noise.
Right.
So when we say signal noise ratio of 60 dB, that means like it's cleanest speech.
Right.
Cleanest speech recording. When we say something like 10 dB,
It's pretty noisy.
That's kind of moderately noisy case. Like situations with 0 dB, that's like severely noisy case. That's minus 6 dBs. Humans don't understand what.
Right. I see.
Typical is in our environment.
Yeah, so we haven't measured what was available. So the question is, what are the typical SNR values for your training data? So we haven't measured it.
I understand that during training you were expanding your training set and noise and various.
Right, and then yeah, I mean yeah, in the test data we don't know, just because we don't have access to I mean these were recorded inherently in noisy environments, so there's no clear way of measuring it, right? So I mean, and also I didn't even think about measuring it. But even if I wanted to measure, I'm not sure how I would go about it because I don't have like a ground truth for these, right? It only comes in noisy, and I don't know what the noise component is and what the signal component is.
It's funny. You run first B, then you detect boundaries of your speech portion, then you estimate the power of noise you can silent region, then you do like a ratio of something plus noise, assuming that the noise kept being
right. So then I see. So the fundamental assumption is that your clip has some parts that are silent, so that you can estimate the noise from there, and then the rest of it you can. Yeah, I think that's doable. No, I mean we haven't quantified that at all, but just by listening to them, they're like some stuff is actually barely recognizable. So I would say, in that barely recognizable, yeah. Sorry, go ahead. Correct. Okay, that's a good question. So, so that's a graph of the accuracy versus epochs. It shows more than 91% because this is I don't have access to the test data. So Kaggle keeps another set of test data. So this is my validation data. So I can only validate it on my own validation data. So when you actually submit it into Kaggle, you get slightly lower results. So that's the only reason. Yeah, exactly. So it's a validation. Yeah, sure, go ahead. To update the student network or the teacher network, you have to look into the difference between the difference between what the student is predicting versus the teacher is predicting. So let's say you have some unlabeled data, right? You add some noise to it, and now you present both of them to the student and the teacher. And the student and the teacher would come up with different outputs, right? And then, so the student would have some distribution for its outputs, and then the teacher would have another distribution for its outputs. And then you just say, okay, I want you to take the KL divergence between these two distributions, and then use that as a loss to update your student network. Does that make sense? Or? Okay.
I wanted to understand how you superimpose this new teacher's portion on top of your neural network. Was it like after this teacher slash student block? Was this kind of appended after the existing?
Right. So I think the question is, so in the whole pipeline, where does it stand, right? So here, the box that's shown with data is the network itself. So so I just try to represent it as, you can't put anything in that box, right? It can be any network. So so this technique you can just pretty much apply to anything you have.
And how much was your improvement not using this new features?
Right. So so that's this plot. Yeah. So the green curve shows the mean feature, the red curve shows without.
Why does one not need labeled data?
Well, you need some labeled data, right? Because at the end of the day, that's how the teacher learns from the student, right? Because the student, you need to have a student to come up with a teacher. So how you do that is with the labeled data. So if you have zero labeled data, then you're kind of stuck, right? Because there needs to be some signal.
Can you do this? I mean, can you use this with time series as well?
Yeah, I mean, with anything. Yeah, I mean, with any model, you would be able to. Yeah. Sorry, that wasn't the question there. Yeah.
So this you apply only on the after software layer, only by classification, or do anything middle combination layers as well?
For the loss, it's only through the outputs, the softmax layers. But how you come up with the teacher is basically you take all the parameters in the student, so all the column weights and everything, and then you do an exponential moving average to come up with the teacher. So
All the way.
yeah, all the way. So teacher is basically a copy of the student, but over time. So it's like an ensemble over time. Sorry.
So when does this student teacher model? So you assume it only looks as unsupervised data. So during training time, does it come after you have exhausted all your labeled data?
Right. So the question is, how do you present your unlabeled data to this? Do you present your unlabeled data after your labeled data, or does it come in? So what you do is in each batch, actually, I mix labeled and unlabeled data. And so there's a specific ratio, and you can kind of play around with the ratio. I think I use like maybe half and half. Yeah, right. Yeah, and then so half of your data in each mini batch is labeled, and half of your data in each mini batch is unlabeled.
First, you will see labeled data and then unlabeled data, or is it mixed?
So it will be mixed, right? So because I'm presenting both in one mini batch, the signal that's going to go back is actually from both. Yeah. Okay.
So do you pick students to make them part of the teacher, or you just train the student network and then it becomes part of their software?
Yeah, exactly. So you just keep training the student as if the teacher was not there, and I mean the teacher comes into play when you're backpropagating, of course, into the student. But then you keep you keep averaging into this teacher.
For every mini batch, you are adding.
At every iteration, yeah. So after each iteration, you would update the teacher. Oh, sorry.
This is an implementation question. I don't know if that's
Sure.
being covered here, but because of the student-teacher backpropagation, can I do latency overall, or how does that perform?
So the question is, does this additional thing from the teacher add any latency to your training? Is that correct? So yeah, I mean you have to do some more additional computation, but I mean it's worth it for sure. Yeah, I mean it does add some, but it's not like terrible. Yeah, good. I'd say probably like around 200 epochs we're kind of done, right? Yeah, but I mean, just I was just making a habit of running them so that I would understand like what's happening in the system. Sorry, quick question.
Okay. Just to after this question, let's finish up the slides and then we can have in continuation. Yeah.
It's not like that you start since the beginning to the teacher.
That's correct.
You could actually maybe train a little bit normally and then start. Once the network is a little bit more certain about.
Yeah, that's a good point.
Should you try that?
Right. So so the way of doing that is, so the question is, we can train the student before introducing the teacher, and only after a while we can kick in the teacher because that student will be more certain about what's happening. So there we control that with this alpha parameter. So if that alpha parameter is close to 0, then or sorry, close to 1, you're just gonna get your teacher is just going to be your student, right? So you just take that parameter and then you slowly ramp it up. So that's exactly what you do, but in a more like gradual fashion. Okay, so it's already 7:30. I'm gonna be a little bit faster over here. Do you have until 8 or? We need to be outbid. Okay, cool. So so next part is about population-based training, and then this technique really handles hyperparameter tuning. And anyone who's done any kind of deep learning model is aware that the first thing that you do is that you try to come up with some papers to understand, you know, what are some good hyperparameters so that I can start training, and then if I can see something, and then you kind of go from there. And the problem is that you have so many hyperparameters that if you start to do a grid search, then you know your computational time starts to explode pretty fast. So so there have been methods that have been proposed for coming up for dealing with this, other than grid search. So you can do some sort of Bayesian optimization. So you're not just doing casting a grid net, but you're making more of a informed decision on how to change your hyperparameters. Also, another technique, and this was actually proposed by, I mean, I think it's been proposed by many people, but there was a recent paper by DeepMind. And so here I'll just show you an implementation of that that's a little bit different. And what we're planning on is we're trying to open source hyperparameter optimization techniques. So hopefully we'll have one package where you can choose between these different techniques. Depending on the resources that you have, you can use any one of these techniques. But I'll specifically talk about population-based training. So in this case, what we do is we have access to a cluster, which we have mini machines on there. And in this specific case, I'm just going to show you how we optimized between learning rate, dropout, and this consistency loss, which is between the teacher and the student. So what we do is we first do a random search, so to speak. So just so that we're clear, I'm going to show two hyperparameters, the dropout and the learning rate. Dropout is on the vertical axis and learning rate is on the horizontal axis. And each one of these red dots represents one model, right? So this is a copy of the model that's at different hyperparameters. So we initialize these 50 models that are shown in red, and then we run each of these models, right? And after 2 epochs, we don't run the whole way. After a couple of epochs, we evaluate this on a validation set. So now, from that 50 population, we know how they've performed, right? So the plot on the bottom right-hand side shows the frequency of the population versus the validation score, and the validation score is only up to 86%, I believe. So a lot of the population is actually falling below 86%. Then what we do is that we take the most successful models out of here, and then we kind of perturb these hyperparameters that we want to learn, and we just perturb them just a little bit. So this is kind of like doing a mutation, right? And then after perturbing, we come up with new hyperparameters, and then on the hyperparameter space, those are shown as the blue dots. Okay, so now we have different models that are these blue dots, and we run those models for a couple of more epochs, and we evaluate them. So now we see that our whole population is actually performing a lot better, right? So the curve has moved to the right. So I think our best model is now performing like a little bit more than 92% right now. Again, we take the best models, we perturb them, and then again, that's shown with the blue dots, and then the old ones are shown with the black dots. We perturb them, we run them, we evaluate them, we perturb them again, so you kind of get the idea. So we do this over and over again. So every couple of epochs, we will do this. The nice thing with this is that by the time you're done, right, you have spent the exact same amount of time that you would have otherwise spent on your model, given that you have the machines to parallelize. And you can pretty much go and cherry pick. Okay, I want this model. It's just the best model at the end of the day. Another nice thing with this technique is that you can see that the hyperparameters at each epoch are different, right? So it's a dynamic thing. So this technique would come up with its own learning rate schedule. So typically what you're going to do is, for example, you'll have to come up with your own learning rate schedule, or typically with the dropout rate, you don't actually use a dynamic dropout rate, you use a single dropout rate. But here, for example, the system has learned that it's supposed to start with a low dropout rate, and as the network gets trained more and more, it will need more of a dropout rate to generalize better for them. So it's kind of like increasing the dropout rate. So so that's the nice thing about this. And if you have the computation tools and if you have the framework, it's pretty much you have your network and you can just plug it into this. Say I want to optimize these hyperparameters and then go. Sorry, question?
I understand the process. How long take you to run the data set to go?
Yes.
Where are the resources?
So yeah, the question is how long did it take me to run this?
And the resources, the computer
So the
computing resources.
how much computer resources? Yeah, we have a cluster. So we have, I don't know, like 70 GPUs, something like that. And yeah, I mean, hopefully they're going to be soon, like our neural processors. But yeah, so you would have to have those resources if you have access to it. The way to do this without those resources, so you can't trade off resources with time, right? So you can do this on a couple of GPUs, but then it will have to you'll just have to do 2 networks, cache them, do another 2, do another 2, so until you go through the whole population, right? So this only makes sense if you have a big cluster. Yeah. Yeah, it takes about a day. I mean, because the normal network takes about a day to train it, because there's no difference between training this way and a normal way. Because what you do is after 2 epochs, you don't start the models from scratch again, right? You just continue training. So by the time you're done, your training is done, basically. Yeah, you don't have to start from scratch again. Okay.
So what parameters would you use for the final one, for example, dropout?
For the final model, I don't need to actually use a specific thing because my final model is now trained. I can only do inference, right? So none of these make any difference. Like, so I'll just take my final model that performs best, and I'll just use that for inference. So the learning rate dropout is only used during training. Does that make sense? So
Normally, when you're doing inferencing, you will divide the output where the dropout layer is. You're going to scale that. So if your dropout during training was fine, during inferencing, you are going to scale it, right?
Right. So, but for that, we know your final dropout rate, right? So you can just use it.
How much performance improvement?
How much improvement do we see?
Yeah.
We don't. So actually, before I use this, I hand-tuned this, and it was very painstaking. This gave just a little bit better than the hand-tuned model. So, but then you just saved a lot of time, basically. And I'll just talk about that, like saving time on using this. But so you can get as good as like a hand-tuned model. And Google folks actually show that you can get even like for reinforcement learning, especially. Apparently, it can do a lot better than hand-tuned models. So there are different ways of visualizing, what has happened. Also, there are different ways of picking this population. So, like in the previous case, I just picked the best ones. But then you can also, do some sort of distribution and then say, okay, I want to pick with the probability that's proportional to the fitness. And picking the best ones gave better results. And also, it's interesting to kind of see how these hyperparameters evolve, right? So you can kind of see that the model has come up with the technique for starting from a high learning rate and then slowly decreasing it as time goes by, which is very typically done. So it's just interesting to look at these plots, but there's not much more to these plots than that. So you can kind of like evaluate different population picking methods, again, by trial and error. And of course, the population size that you have does matter. If you have a larger population size, you do converge in better results faster. So And then that's also like a time resource trade-off in this case. So I'm pretty much done. So I'll talk about the use case right now. So the model that I've just shown and that was just trained actually was a huge model, right? So it's kind of got out of the spirit of the competition itself, because the competition was about coming up with a small model with low latency. But then, we just started building this model larger and larger and larger. So now it's a huge model that's about 250 megabytes. That's getting about 90% accuracy. And if you wanted to deploy this on an edge device, you just cannot do that. So there are ways of taking a large model and then pruning it down. And people use like low precision techniques and pruning. Another thing that you can do is to just use population-based training and come up with a small model that you think is going to be okayish, and then just give it to the population-based training and then let it optimize for you really fast. So with some of the folks at Intel that work on the speech accelerator called GNA, these are in Celeron processes, we wanted to target that specific speech accelerator. So we wanted to come up with a small model really fast. So this just took us a day to do this. So once you have the framework, you can just plug in a very small, lightweight network, and then come up with this model B that gives you slightly lower accuracy, but it's a lot smaller in size. So this was about 1.5 megabytes. So so the idea was to have this small, accurate, and fast model, and then we can deploy that for very low power and low latency applications. So again, as I said, you don't want to be talking to your robot and then if it needs to stop right now, it stops 5 seconds later. So you want to have that, and then you don't want it to be burning power. So I'll just show a very quick demo on like how that network, the small network performs. So we're just going to be playing Pac-Man with the voice commands, and again, it's because I have the microphone, it might get confused or whatever, but it does a good enough job to be able to do things. So right, up. Oops. Okay. Well, so we can try again. Left, right, up, left, stop. So it does decent. And then this model was never trained on my voice. It's just specifically from the speech commands dataset, right? So it's never heard my voice, and it wasn't trained on that. And another nice thing with this method is actually if you deploy this using the semi-supervised methods, what you can do is that, if, for example, if you had this arcade game and then people are trying to play it, you can record people's voices and then feed it into the system to train it more and more. So over time, the system will actually get better and then get adapted to the people who are actually using the system itself. But as you can see, it's small enough and it's fast enough to be able to be used in an actual application. Sorry, go ahead. That's a question.
How do you solve the one stack on doing some enveloping?
Yeah, so what I do is I will just sample every 100 milliseconds. And so I have a 1 second window. It gives a classification. I'll move it a little bit, right? It gives another classification. I'll move it a little bit, gives another classification. And then you can say, okay, if you classify the same thing 3 times in a row, then I want you, then that's the classification. I mean, in this case, actually, it's just one. That the first thing that it comes, it will classify that, and it's still pretty robust. Yeah. Sorry.
In your model A and B, can you give a scale of how many attention blocks that you have?
There are no attention